Here. Today we are going to be doing a very popular Leetcode, and that is Leetcode 146 LRU Cache. LRU stands for least recently used, if you're not aware. And yeah, let's hop right into it. This is a very popular programming question that is quite difficult, hard. I don't think unless you've done it before, I don't think you have a really good shot at doing it. And 1 second, let me just make sure that I have started. Oh, there we are. And yeah. Yeah, and I've personally failed it in interviews as well. But it's a very interesting problem, and I think once you have a good grasp on it, it is interesting to think about with data structures and algorithms. It's something interesting to kind of think about. So with that, let's hop into what does LRU cache actually mean. So LRU is a type of cache replacement policy, so just reading right off Wikipedia here. In computing, cache algorithms, also frequently called cache replacement algorithms or cache replacement policies, are optimizing instructions or algorithms that a computer program or a hardware-maintained structure can follow in order to maintain a cache. Hey Pulsating, thanks for stopping in today. And let me just turn down the volume. So to manage a cache of information stored on the computer, when the cache is full, the algorithm must choose which items to discard to make room for the new ones. So least recently used, let's hop into one right here. So this is the example on Wikipedia. The access sequence for the below example is A, B, C, D, E, D, F. So this has a capacity of 4. We added A, and it becomes rank 0. Then the B is added next, as you see here. And so we have A, B, A with rank 0, B with rank 1. Add the C, becomes rank 2, and D becomes rank 3. The interesting thing happens when we add the E. We need to now replace something, and we replace the least recently used thing. So A was A rank 0, you replace the lowest rank, and then E is now added where the A was. When we add the D, D's already in there. It's already in the cache. But it was rank 3, but now it becomes rank 5. So it's kind of been like refreshed. It's now the most recently used thing. And then when we add an F, well, we need to replace the lowest ranked thing, and that is now a B. So it becomes E, F, C, D for the final answer. So to do this, I'll just kind of spill the beans right away to make sure that we have time for debugging. Before I do that, let's actually walk through the problem statement in Leetcode. So it'll design and implement a data structure for least recently used cache. It should support the following operations: get and put. Get of a key gets the value, will always be positive of the key if the key exists in the cache, otherwise it will return a -1. Put the key value will set or insert the value if the key is not already present. When the cache reaches its capacity, it should invalidate the least recently used item before inserting a new item. That was that A being replaced that we talked about before. The big thing is, could you do both operations in O of 1 time complexity? So if you have some familiarity with data structures and algorithms, you see a get, okay, you get the value, and you want to do that in constant time complexity or O of 1 time complexity. Well, you just think a dictionary, and then that is the case. But with just a dictionary, you would be unable to keep track of things. You want to use a different data structure to complement the dictionary. And here we're going to use a doubly linked list, and I'll get into a little bit more of how that works. But let's go through the example right here. So we instantiate a LRU cache with a capacity of 2. We put a key value pair of 1 and 1 in. Then we put a key value pair of 2 and 2. So at this point, at the end of the second line, the put the 1, 1 key value pair is the least recently used. But once we get that, well, first off, we're going to return a 1. But when we put the 3, 3, we evict now key 2. Because by getting the 1, we kind of refreshed it. Then if we get the 2, well, it's not there anymore because it's been evicted. Then if we put the 4 in, then we get rid of the 1, 1. So we have 3, 3, 4, 4. We get the 1, it's no longer there. We get the 3, it returns the 3. Get the 4, it returns the 4. So let's hop right into it. We're going to use something called a doubly linked list. So we're going to have that class. It's going to have a node, and in an init, it's going to take a self and the key value. And for those of you not familiar with Python, self is similar to this in a few different languages, such as JavaScript. So self.key equals key, self.value equals value, self.prev equals none, and self.next also equals none, not non-d. So let's hop to the big board real quick. So in a singly linked list, which you may be familiar with, we just have nodes and they point one way with usually a next is what you see. And a doubly linked list, as you can imagine, in addition to the next, now we have prevs. So that's all we have. And to init those nodes, we say their next and their prevs are none to start. So let's hop back in to the code. So we're also going to have that LRU cache as a class. That is also going to have an init. And that's just going to take a capacity. And we're going to say, well, the self.capacity, so we can use that elsewhere for this instance. That's going to be the capacity. We're going to instantiate that dict like this, which is not technically correct. I don't think you should write self.dict for this because I think dict is reserved, but I think it works for now, and that's the way that I'm used to doing it. Oh, by the way, I'm recreating a Leetcode solution by a user called Susie. So thanks a lot to Susie, which was a very interesting one. Yep, and then we're going to have the self.capacity, the self.dict. Now we're going to have heads and a tail, and those will be instantiated as instances of nodes with key value pairs of 0 and 0 each, and that'll become a little bit more clear while we're using those in a little bit. And the head next will point to the tail, and the tail previous will point back to the head. Good. So we're going to want to have two helper functions for this, and that we're going to want to help to keep things as refreshed as they should be. So we want to have a remove first, and then we want to think about an add. So let's go to the big board. So if I'm given a node that I'm passing into an underscore remove function, how do I actually remove this node? With a doubly linked list, how you do it is, or one way to do it, is to find, well, what's the previous of this node, and you can just do that by saying previous equals node.previous. And what's the next of this node? Find that very similarly. And then you just rewrite. Well, so the next of the previous points to node. But if we say instead of that, if the next of the previous points to the next, and for the next node, if the previous of the next points to the previous, well, we kind of bypass this node. It's it's pointing out, but it's not, nothing's pointing to it. And so for all intents and purposes, it's gone. She gone. So that is no longer there. So that's how we write a remove. So let's get into it. So the remove, we'll just take a node and we'll just do exactly what we just said. So the previous equals node.previous, next equals node.next, and the previous bypasses the node. So the previous.next was previously the node. It can get a little confusing here. But now the previous next now equals the next. And the next.previous was the node, but now the previous of the following node will become the previous. And that's all there is to the remove. Come on, have a quick drink of water. Then we have an add. So we're going to be adding to the tail, and I'm going to go to the big board for this one as well. But that's also going to take a self and a node. And so how are we going to add? So we're going to add from the tail, and we're going to pop from the head, which I think is a little bit backwards, but you should be comfortable doing both. So we have head, we have a head up here, and we got a tail all the way back here, huh? And in the sake of brevity, I won't draw both arrows for this, except for these last two, because we're going to be adding to the tail. So we know what the tail is. It's called the self.tail.previous, and those kind of like stay as like little landmarks. So here's our tail, and let's say we want to add a node here. So this is called the tail. We can find this previous because that's just self.tail.previous, so this becomes a previous. And we have our node here. So how do we insert this? How do we add this to the tail? I can see now it's a little small, but it's the best we got, damn it. So what we're going to do is just say, well, the previous, we know what the previous is. The previous dot next is going to equal the node. The tail.previous is also going to equal the node. And then we just draw it from the node. Then the node.previous equals the previous. And then the node.next equals the tail. And that's how you do an insert with a doubly linked list. Or an add. So let's hop to it. So we want to find that previous. That's just self.tail.previous. Then we say, well, the previous.next is the node. And then we say, well, the self.tail.previous now is no longer the previous, it's also the node. Now we have to draw those lines back from the node. The node.previous equals the previous, and the node.next equals the self.tail. And with that, we're done with our helper function. So let's hop right into the heat of the meat. We want to do a self.get, which takes a self and a capacity. That is not how you write this. There are no selves for there. Sorry about that little syntax error for you. Good thing I caught it. And the get does not take a capacity, it takes a key. And all we do with that key is, well, if it's there, we do something, right? So if key in that dictionary, because this is that constant time lookup, we're going to do something. If it's not there, then we do a return -1. But if the key is in the dictionary, well, we want to do that refresh step. So I closed the Wikipedia page, but when we accessed, everything that we access that's already in the dictionary needs to become the most recently used. So how do we do that? We just remove it and we add it back again. We remove it, it gets removed from the linked list, and then we add it back again. It becomes in the most recently used spot by virtue of our addition method. So that's all we do. So we just say node equals the self.dict of key, and then we just remove it, and we just add it back in. And that's all there's to it for a get. Then we need to add the put. So put self key. This needs a value as well. We're not just looking for keys. We're also looking for values. Similarly to the get. Hey, Coder Eli, thanks for stopping in. Similar to the get, we see if the key is in the self.dictionary, because if we put something that's already in there, it needs to be refreshed. And to refresh it, first you need to remove it. So then we're going to self._remove that self.dict of key. So, just a little water for you. These removes look a little bit differently. Up here I assign a node because I use it twice. Down here I don't. So I don't use it twice. I just remove the self.dict of key, not the node. So no need to be confused there. If it's in there, we remove it. And then now we need to add it back in, or add it in the first place. So the node is going to be of the node, an instance of the node class with keys of key, with a key of key and a value of value. and then we just add that in to our linked list, which just add like that. And then we also make the dictionary value for the key that's passed in equal to that node. Because that's, yeah, doubly linked lists serves as the value of our dictionary. That's kind of like the main point of this. Now the put is interesting though, because remember when we got rid of the least recently used things. So when do we do that? We get rid of those if we were over our capacity. So if the length of the self.dict is greater than the self.capacity, now we want to remove the least recently used thing. And like we talked before, we're removing from the head. So if I go to the big board, if I did this step where I added this now, I'm going to remove this node right here. And that'll be redrawn like this. So that's how we remove. We're removing from the head. So to get to the code, if the length of the self-dict is greater than self.capacity, then we also make assign a node. This time the node is going to be that head.next. We're not removing the head or the tail. Those serve as little markers that keep us on the straight and narrow. But then we want to self._remove that node, and we want to delete that key value pair from our dictionary so it doesn't influence our capacity. So how we do that in Python is we just write delete self.dict, and what the key is just the node.key. So we've got about 13 minutes left. I did this problem twice beforehand. The first time everything worked properly, and the second time it didn't. And the second time I couldn't figure out what my problem was, but I think I was messing up myself, like I was doing earlier. So let's take a walk through the code and then see if it works. So the main idea is correct. The syntax might be getting us here. So we're using a doubly linked list to do a least recently used cache. The doubly linked list, we use nodes that have key values. They start off with the key, the self.key being the key, the self.value being the value, and previous and next of none. Then we have an LRU cache itself, which has a capacity. Self.capacity is capacity, self.dict is dict. Its head starts off as a node of key value pair of 0, 0, same with its tail, and its head points to its tail. And those are kind of just like little empty nodes that we use to keep track of things. The self.head.next equals the self.tail, and the self.tail.previous equals the self.head. Before we get into the get and put, let's go to our helper functions. I'm actually gonna, I don't like to cheat on these type of things, but I think, yeah, we're in a good spot. Obviously, oops, going a little banana, something to look right. For function definitions, it's always good to write def. I'm wondering why does this not look right? So when we remove, we find out where the previous is for the node, we find out where the next is for the node, and then the previous next points to the following node, and the previous of the next node points to the previous. So that's how we remove. When we add a node, we find the previous, we're adding to the tail. The previous of the next becomes a node. The previous of the tail becomes that node, and that node points to those two as well. So here's where we want to look at constant time and for getting and putting. If the key is in the self-dict, which is constant time lookup, then the node equals the self.dictive key. So the values are nodes of this linked list. We remove it and add it back to refresh the how recently used it was. And if it's not, we just return -1. Oops. And it's very important to return node.value. Otherwise, yeah, we're not returning anything properly. And then if the key is in the self.dict for a put, this should also be constant time, we remove it. And then if it is or it isn't in there, we make a new node. We add it. We set the value of that key in the dictionary to that node, and if it's greater than the if the dictionary length becomes greater than the capacity, we remove from the front. So that looks to be on the up and up. Let's go ahead and submit the solution and cross our fingers that everything is good. No whammies, no whammies. And it's accepted. So it's surprising. Before this, I'm not sure what I was doing wrong. I think I may have been leaving out this returning the node dot value. But this is a very interesting problem, I think. It's probably one of the most difficult that you'll see for most interviews. It's a Leetcode hard, and like only about 140,000 out of 760,000 have solutions to it. There are ones that are simpler. There's even some in the comment chains for this solution that are simpler, that don't use a head or a tail. But I think that's actually more confusing by leaving those lines out. For me, thinking about, okay, we have these like markers, that's a little bit easier for me to wrap my head around. Some gotchas. Well, I'll also say this as well. In a 45-minute, if you're practicing for coding interviews, you will not see many problems much longer than this, because this is 50 lines of Python. And it's just, you don't have that much time in a 45-minute interview, just like the physicality of writing that much out. You're not going to see that much out. But beyond just practicing for interviews, I think it's an interesting application of the strengths of two data structures, of using a dictionary and a doubly linked list to get constant time putting and getting time complexity. So let's do some gotchas, things that I got hung up before I wrap things up here. Just general syntax things. When you do the init, you have to point your head dot next to the tail, and you have to point your tail dot previous to the head. I forgot that a few times when I was practicing for this one. This time I forgot to return the node dot value. It's silly things like this. I always remember when I do if catches, I think, okay, if you don't hit this conditional, and sorry, I shouldn't say if catches. That's not a real thing. If I do an if conditional, I think, okay, if I don't get that, what do I return? It's always very important to remember what you return if you get it as well. And just general syntax things. There's a lot, once you get a little bit lengthier in these problems, there's just a lot of places to get tripped up. But with that said, this was least recently used cache, Leetcode problem number 146 from Programmer Mitch. Thanks for stopping in this Sunday. I'll be live next Sunday at 6:30 p.m. doing another programming question, and I hope to see you then. I am no longer doing the hot sauce challenge because my stomach was really disagreeing with me. So sorry for people that were tuning in for that. But like I said, that's the end of the show here today. Thanks a lot for stopping in, and I'll see you next time.